Okay, so let's begin with 6.4 notes here. So to start off this section, I want to go back in relating energy to force, right? How does energy relate to force? Well, the easiest way to relate energy to force is through work, right? We know work equals force times the displacement, right? There are a couple conditions here, though. In order for work to equal force times displacement, one, the force and the displacement have to be the same direction, right? Both of those vectors have to be directed the same way. Otherwise, we throw in the cosine or the sine of the angle. And then the other condition is this only works if the force is constant, right? What do we have to do if the force is not constant? And so let's approach that, right? Let's go to that. We've seen before, going back to chapter 4, that what do we do if the force isn't constant? Well, we do a little bit of calculus, right? And the key here is I would think graphically about this. If I gave you a force versus displacement graph, if I give you a force versus displacement graph, then I think hopefully at this point we would all agree the area underneath that curve would represent the force times the displacement, and therefore the area underneath that curve would represent the work done or the energy, right, gained or lost by the system. So that's how I do it, right? If I gave you a function of force in terms of x, right? So if I gave you force as a function of displacement, notice this is not f times x, it's f of x, right? So if I gave you the function of force as a function of displacement here, then that would represent, or the area underneath that would represent the work. So in other words, the integral, right, the area underneath that curve would represent the work. So work as a function of position would equal the integral of force as a function of position, right? More generically, what that allows us to do is say that a change in potential energy as a function of position here will equal my integral of force as a function of position, right? And that's what we're going to step to with this section, because we're going to look back at gravitational energy and how the change in gravitational potential energy actually emerges from this relationship right here. So let's look at that. Let's look at kind of the derivation, if you will, for our gravitational potential energy, right? So we probably remember, you guys probably remember going back to last year, how to find the change in potential energy, but let's look at how gravity and the force of gravity can actually confirm that. So I'm going to start with the key relationship that, again, I know that my change in potential energy as a function of distance, and I'm going to use r here, and you guys will see why I use r in just a second. But my potential energy as a function of r is going to equal the integration of my force as a function of r. And the reason I do that is because we're going to be dealing with the force of gravity here, right? And what is the force of gravity? Well, the force of gravity is our universal constant times m1 times m2 all over r squared. So if I substitute that in, again, my potential energy as a function of r equals the integration of g m1 m2 all over r squared. Well, if I look at this, all of these measurements are constants. G, m1, and m2 are all constants, with the one exception being, right, my r squared. I'm going to go ahead and think of that r squared as r to the negative second power, just because that's going to make it easier to then do the integration here of this, right? So anyway, the potential energy as a function of position equals, I'm going to bring out my three constants, so g, m1, m2 times the integration of r to the negative second, and it is with respect to dr, since both of these functions were in terms of that position, right? So again, bringing this all the way out, how do I integrate this? Well, because it's a negative 2, right, I would integrate that by adding 1 to the power and then dividing by that new constant. So I'd add 1 to that, so now it'd be r to the negative first, and then I'm dividing by that new negative 1, right? So what I end up with then is u of r equals negative g m1 m2 all over r. And this is the definition for our potential energy for something like a satellite if it's in orbit around the Earth or the Sun or whatever it may be orbiting around. Right? So again, that's the definition that we work with for the potential energy of a satellite. The one thing that I do want you to notice is that the definition here does have a negative in that. And that's going to come into play as we see in the next couple slides here, but that actually is a very important conclusion for us, right? So we're just defining, keep in mind, potential energy can be defined with respect to any point. We're just defining some point as 0, and then any potential energy closer than that will be negative potential energy. And you guys will see what I mean by that soon enough as we get to some of the more complicated examples in this fourth section here. So then a few things to note about the potential energy of a particle, right? So the gravitational potential energy here. The potential energy of a particle infinitely far away from a mass is defined as 0. That's actually easy enough to see if we just look back at that equation, right? My potential energy, again, as a function of position, equals negative g m1 m2 over r. If r is getting infinitely big, so if r is approaching infinity, then wouldn't that mean this fraction is getting infinitely small? So in other words, that whole fraction would be approaching 0. So again, we define the potential energy as a point infinitely far away as 0, which allows us to then say we have negative potential energy as we work closer to get there. Because the force of gravity is always attractive, an external agent must do positive work to increase the separation between two masses, thus U becomes less and less negative as R increases, right? So again, this is really trying to emphasize what's going on with that negative in the equation. So the idea there is if you take the Earth and you take a satellite very close to the Earth, right? We know the natural interaction between those two objects, the force of gravity between those two objects, is going to be pulling them towards one another. So in order to resist or change or fight that, right, we would have to be adding energy to the system to move this satellite further away from the Earth, right? If they want to pull together, the only way that we can move it further away is to add energy to the system. And that's why we're defining the potential energy as being negative, right? We know that this point over here is 0, right? If it's infinitely far away, the potential energy would be 0. So then, if we're adding energy to bring it infinitely far away, we're adding energy to approach 0. That means we have to be coming from a negative value, right? So we define this as a negative potential energy that gets less and less negative as I add energy, right? That negative number is going to get smaller and smaller as I'm adding to it until eventually it approaches 0. Right? So these two bullets, which are hopefully seemingly obvious based on the equation, are very important for helping us understand the equation. Again, if we have a point infinitely far away, we define the potential energy as 0, and we define the potential energy as negative because it takes positive work to move a satellite further away, right, from the object that it's orbiting. Okay, so both of these conclusions are very important for us establishing kind of the context behind a lot of what we're going to do here in this section. Okay, so one of the biggest themes from the questions that we're going to see in this section here are, can we find the total mechanical energy of objects in orbit, right? And keep in mind, this is including whether they're circular or elliptical orbits, right? So how are we going to do that? How are we going to approach that? Well, the first and foremost, right, when you see total mechanical energy, hopefully at this point we're getting comfortable that the mechanical energy represents all of the potential energy plus all of the kinetic energy, right? The only form of energy mechanical energy does not represent would be something like heat or chemical energy, right? So anyway, that's what we're looking for. We're looking for how can we find the total mechanical energy? Well, the obvious answer here would be if we could just find the kinetic energy and the potential energy and add those two together, right? We also know that energy is being conserved as long as there's no outside force, and since the force of gravity is a mutual force between the system here, there isn't any outside force, right? So my change in energy, if energy is being conserved, my change in energy better be equal to 0, and therefore the change in total energy would equal the change in kinetic energy plus the change in potential energy, right? So in other words, the change in kinetic energy would be equal and opposite to the change in potential energy, right? And simplifying that maybe a little bit more, we'd know that if I was gaining potential energy, right, I'd have to be losing kinetic energy in order for that to happen, right? The energy has to come from somewhere, so I'm either adding potential energy at the cost of kinetic or vice versa, right? So anyway, a few of the relationships that we need to be comfortable with. We're also going to see how we can represent the total energy in terms of just G, our universal constant here, the mass of the planet, the mass of the satellite, and R, right? So our goal with this next part here is going to be, instead of using like 1/2 mv squared or those measurements, how can I represent the total energy of a satellite in terms of these 4 variables? Okay, so to see that, let's start here with a relationship we've actually used a couple times before. We know that if a satellite is in orbit around the Earth or the Sun or whatever it may be, right, in order to follow a circular or a semicircular path here, there has to be a centripetal force, right? And the only force that's possibly providing that would be gravity. It's not like we have some giant rope or spring or anything like that, right? So the force of gravity is what's providing that. So we've seen this relationship before, right? If you recall, we actually saw this to help us find the orbital velocity for a satellite. But instead, we're actually going to stop this one a little bit short, and you guys will see what I mean by that here in just a second. Okay, so instead of taking this all the way, if I know that this relationship is true, I'm going to go ahead and cancel out the r from both sides, but I'm actually not going to cancel the mass of the satellite out. And here's why. So I've got g m1 m2 over r equals mv squared. The reason I did that is, doesn't this look awfully close to something that we know, something we just talked about, right? Isn't the kinetic energy 1/2 mv squared for that satellite? So this is representing then 2 times the kinetic energy. Well, let's just multiply both sides by 1/2. So if I multiply both sides by 1/2, then this would be 1/2 over here, and I would add a 2, right? Multiplying this by 1/2 would add a 2 to the denominator there, right? So what does this tell me? Well, this tells me then that the kinetic energy of the satellite can be represented as g times m1 times m2 over 2r, right? So the mass of the satellite, the mass of the planet, over 2 times the distance between them, right? So that's a representation of the kinetic energy in terms of g, m1, m2, and r. So then if I take that kinetic energy, right, if I substitute that value in for my kinetic energy down here, what do I get? Well, again, the total energy of the system would equal the kinetic energy, which we just said is g, m1, m2 over 2r, and then plus the potential energy, but keep in mind we just defined the potential energy as negative g, m1, m2 over r, right? So then if I do just a little bit of combining like terms here, first thing I've got to do is get a common denominator, so I'm going to multiply the top and the bottom of this fraction by 2, and then I'm going to find that my total energy equals negative g m1 m2 over 2r, right? Getting that common denominator, so now it's 2r. And that's the total energy for a satellite in circular orbit, right? So if they ever ask us to find the total energy of a satellite in orbit, all you really have to do is calculate this value right here. Now, obviously, it's very helpful to know where that equation comes from, but again, all you really have to do is calculate and plug those numbers in. What about if it was an elliptical orbit and not a perfect circle? Well, just like before, just like we saw for the period, the only thing that changes if it's an elliptical orbit versus a circular orbit is we replace r with our semi-major axis, right? Keep in mind for A, that is half of the major axis. So the major axis is that largest distance throughout the ellipse there. The semi-major axis would be half of that. So again, for the elliptical path, the total energy at any point would be negative g m1 m2 over 2a, or in other words, over the major axis, right? 2a is the major axis. But a very powerful conclusion, because again, the significance here is this gives us a way to find the total energy at any given point on the ellipse, right? So if I ask you what's the total energy of the satellite up here, we're not going to try to find the potential energy plus the kinetic energy at that location, because finding the velocity at that location would be a challenge. Instead, we're just going to take advantage of using the total energy as this representation. And then since we know that the energy is conserved as it goes throughout its orbit, right, that total number stays constant. Okay, so then the last major concept here in this fourth section, and then the rest of this section will be working examples. But the last major concept is what they refer to as the escape speed. And the escape speed, I'll give you guys obviously pause if you'd like to read through this, but in simple terms, the escape speed is how fast does something have to be launched from the surface of the Earth or whatever it may be, right? How fast does something have to be launched vertically so that it can get infinitely far away from the Earth, right? So we know in order to lift itself up, right, we have to be adding energy to the system because it's going to be gaining potential energy. So how fast, how much kinetic energy does it have to have in order for it to do that? Well, again, the key to solving this problem becomes we're going to use energies to help us out, right? So I'm going to jump down here and I'm going to use energies to help me out, right? Since we know that energy is conserved, the energy when we launch it is going to be equal to the energy when we're infinitely far away. Well, let's start by thinking about the energy when we're infinitely far away. We know the final potential energy at that infinite location would be 0. If this is the minimum speed, we also know the final kinetic energy would be 0, because if we're finding the minimum speed, the minimum amount of energy required to escape the Earth's atmosphere, then at that point when it reaches infinity, right, it's not going to have any energy left. It's just going to be, it's going to end up having used all of its energy, right? So its final total energy would be 0. So then what that tells me is the initial kinetic energy needs to equal the opposite, right, of the initial potential energy. And we'll see the rest of this worked out in the second part.